Hi, my name's Elizabeth Polgreen, and I'm presenting work on our experience of using model checking to triage the severity of bugs in the Xen hypervisor. This work is a collaboration between security experts, formal verification researchers, and people with expertise across both areas. Most systems have layers of security. This means that few bugs are critical, but determining which bugs are critical is difficult. And in principle, model checking can be used, but software is often too big for the state-of-the-art tools. So in this talk, I'm going to discuss our experience of using model checking to triage the severity of security bugs in the Xen hypervisor, which is the hypervisor that runs many AWS cloud services. And I'm going to detail the adaptations necessary to CBMC in order to scale model checking to a code base of this nature. So first, I'm going to give a brief overview of Xen and talk about how security issues in Xen are manually triaged. I'll discuss why model checking Xen is difficult and what we did to make it possible, and I'll finally talk about what happens now if a security issue is found and some open problems in the area. So Xen is a hypervisor. That is, it's software that creates and runs virtual machines. Amazon use a customized version of Xen on some of their EC2 servers. And we picked Xen for this work because it's both relevant to Amazon and open source. But we believe the adaptations we made to CBMC for this work will be useful for other code bases. So a hypervisor partitions one machine into multiple machines. Each machine looks to the user like a single machine with its own OS. Xen is bare metal, so it sits directly on the hardware of the host and manages all of the host resources. An example of a hosted hypervisor would be VirtualBox, which runs on top of the OS of the host. So a key job of Xen is keeping guest memory isolated from other guests and keeping hypervisor memory isolated from guests. And bugs in Xen could result in malicious guests being able to steal user data or to perform denial of service attacks. And so what happens when a bug is discovered in Xen? So typically what happens is that the bug is responsibly disclosed to the Xen project. Then the Xen project release an XSA, a Xen Security Announcement, to members of the Xen project, usually roughly 2 weeks before the general public release of the bug. And this gives members of the Xen project 2 weeks to perform mitigations. And what is an XSA? It's a text description of the problem, along with a patch that fixes the problem for specific versions of Xen. So this here is a text description of an XSA which describes a memory leak that occurs when part of Xen fails to ignore legacy operand size overrides. And the key thing is the patch that comes with it fixes the problem for a specific version of Xen. And Amazon run a customized version, which means that they may not be able to apply the patch out the box, and they may not know whether the problem described in the XSA actually affects their custom version of Xen. So these XSAs become publicly available after the embargo period. So if you go to the XSA release website, you can see these text descriptions. And when I recorded this talk, you can see that there are a number of XSAs that have been pre-released but embargoed. So you can't yet view the description or the patch, but you can see they've been assigned a number. And members of the security operations team triage potential security bugs as they're discovered or reported. And they must determine if the bug is critical. That is, if it represents an immediate security issue that might affect AWS users, or if the fix is less time critical. If the bug might be critical, then the team must make a decision about whether to page the engineers responsible for this code and wake them up. And often, the same bit of code is used in multiple products, and the defenses might differ from service to service, so the team may find themselves needing to wake up quite a few engineers from quite a few different teams. So clearly the question of when is a fix urgent is important to answer accurately. So when is a fix urgent? I already mentioned that most bugs are not serious security issues. That's because most systems are built with many layers of defense. A bug can affect one or more of these security layers, but as long as some layers remain intact, the bug does not expose the vulnerability to the outside world. In practice, the more layers of security that are compromised, the more severe the bug is, with the most severe case being a bug that compromises all layers between secret data and a malicious guest. And how do Amazon currently determine if a fix is urgent? Well, mostly by an expert engineer sitting and thinking about it and trying things. Some of my co-authors on this paper have decades of experience working on the Linux kernel and on Xen, and they really are true experts. And as part of determining if a fix is urgent, these experts will construct security tests, which are essentially a set of test inputs that will trigger the vulnerability from a test harness. Realistically, this is actually more of a cycle of try something, repeat, try again. But eventually they may manage to trigger the vulnerability through several layers of security and determine that the fix is urgent. These tests are hard to come up with by hand though, particularly for issues which involve getting precisely the right inputs to trigger precisely the right overflow. Okay, so this is difficult and it requires really expert experts. It's potentially time consuming and done under intense time pressure. So, can we use model checking to help? The first thing to note is that this is essentially a reachability problem. Determining how many layers the bug compromises is equivalent to finding out whether you can get from one place in a program to another. And essentially this is what the security tests try to do. They try to establish the reachability of a bug from a given test harness. But can we do the same with model checking? Well, the first step is we need to specify the point that we wish to establish reachability for. We're using a software model checker, so we need to write an assertion that represents the security issue in a given XSA. This is fairly straightforward. The XSA description makes it reasonably easy to write an assertion, even for a non-expert like me. So in the example we looked at, we know the operand size is assumed to be always 8 or 16, and the memory leak is triggered when the operand size is not 8 or 16. So this is the assertion that we write. Obviously, placing it in the code also requires some careful reading of the description and of the patch. So we've built an assertion, now let's just use a model checker, right? Well, so first you have to get your code in a state where your model checker can parse it, or you have to get your model checker in a state where it can parse your code. We opted for the latter. It took a while. The model checker we chose is CBMC, which is a bounded model checker for C programs. It's been used on automotive code and to verify Linux drivers and on some existing Amazon code, so it seemed like a good choice. Plus, we had two of the main CBMC developers to help us. But CBMC doesn't typically get used on this type of low-level code very often, so we uncovered a few bugs. But we got there eventually, and here it is. There is now a Xen compilation and parsing integration test for CBMC, so you too can run CBMC on Xen. So now we've got an assertion, and we've got a model checker that can parse our code, so we just run CBMC, right? Well, no. So I ran this over the weekend. I started it on a Friday afternoon. I went out and had a nice weekend, and I came back to it on Monday morning, and CBMC hadn't even started constructing the SAT formula. So typically that's a bad sign. If the formula is so big it takes more than a weekend to build, it's probably too big for the SAT solver too. CBMC has some built-in program slicers, which are designed to reduce the size of the codebase by removing code that's not relevant to the properties being verified. So we tried those. The first one we tried is the Reachability slicer, which removes code on the control flow graph that is not reachable from the entry point of the program and is not backwards reachable from the assertion. The Reachability slicer is very quick, but sadly the codebase is still too big to be analysed by CBMC. So then we looked at the global init slicer, which removes unused initialization code for global variables. This made very little difference. Resulting codebase, still too big. Then we looked at the full slicer in CBMC, which precisely computes the cone of influence. That is, it calculates the lines of code that the property depends on. It sounded promising, but sadly the cost of this precision is that it just takes too long to run, and it also didn't finish over the weekend. So why is this so hard? Well, there are a few reasons. It's a big code base. It's about 800,000 effective lines of code, and by verification standards that's pretty big. And we're looking for long counterexample traces. There are function pointers everywhere because Xen is a highly configurable code base. So that makes this code base pretty broad, and the function pointers are configured by the boot code, which we can't analyze because the boot code contains a lot of assembly code. So we don't know what these function pointers point to. So we have to take a guess and assume they could point to anything. And finally, there's more assembly code in Xen than just in the boot code. And there isn't a verification tool that handles assembly code and C code and is scalable and robust enough for this work. So let's talk about how we addressed these challenges. Well, I modeled some assembly code by hand. We improved the function pointer removal in CBMC somewhat to cope a little bit better with this problem that we can't analyze the boot code. And then the key adaptation we made, we introduced an aggressive program slicer, which reduces the size of the code base at the cost of precision and approximates the removed code. And this really made the difference between a verification problem that doesn't finish in 48 hours and a verification problem that terminates in under an hour and sometimes in minutes. And we also spliced in some code harnesses so that we can start the analysis without analyzing the boot code. So let's go through these in more detail. First, the easy one. Modeling the assembly code in C was a manual task, but there wasn't very much of it. And one of the key things we modeled was the code that gets the input from the guest. And we treated any values that are provided by the guest as non-deterministic. So this modeling will be reusable for future XSAs. Function pointer removal. Honestly, the function pointers were probably one of the biggest challenges here. The whole of Xen is configured with function pointers, and these cause real problems for verification. And in part, this is due to the way CBMC handles function pointers, which is somewhat dumb. So basically what it does is it goes through, and for every function pointer, it replaces it with a big switch statement over all of the functions that have the same function signature. And in Xen, there are a lot of functions with the same function signature, so this could be replacing one function pointer with a switch case over 300 different functions. And then later on, during symbolic execution, CBMC will determine what values the function pointers can actually take. But our function pointers are set in boot code, which we can't analyze, and so we're stuck with these huge switch statements. So one of the things we did was implement a basic flow-insensitive alias analysis, which goes through the code and looks for all of the assignments to these function pointers, and then replaces this switch statement with a switch statement over these assignments. And this reduces the size of the switch statement a bit, which makes a bit of a difference to the breadth of the call graph of Xen. And it also reduces the number of potential spurious counterexamples caused by this over-approximation that happens in the function pointer removal. Now, the changes I've talked about aren't enough to enable us to run CBMC on Xen, so let's move on to the real meat. Let's talk about the aggressive slicer. This is the key adaptation we made that allowed us to run CBMC on Xen. We looked at the existing slicers and we found that they either didn't remove enough code or they didn't complete on Xen. So we introduce a new slicer which aggressively removes code, including some code that might be relevant to the property. This allows us to analyze part of the code base and then approximate the remaining code that's been removed by the slicer. And this achieves scalability at the cost of precision. So we also allow this to be configured by engineering input to tailor this precision loss. Now, the aggressive slicer works on the call graph. So this is the call graph of Xen. This is not the control flow graph, this is the call graph. It's quite big. It's really, really quite big. So I think this gives you a real idea of the scale of the problem here. This has 180,000 function calls in it. So the first thing the aggressive slicer does is it constructs the call graph. So let's look at this tiny subset of the Xen call graph, and you can see that I've added in an assertion for an XSA, and I've also added a harness as an entry point. We'll come to the harness later, but for now just treat it as the entry point to the code. The first thing the slicer does is find all of the direct paths from the entry harness to the assertion on the call graph. Here there's only one. Now we mark any function that is not on the direct path as a function that should be havocked, and then we havoc them. And what do I mean when I say we havoc them? What we do is we remove the body of the function and we then approximate the function based on the function signature. So the basic approximation that we use is we assume the return and any modifiable arguments can take any value. That is, we assign non-deterministic values to the return and to arguments passed by pointer. And so this is a crude approximation, and it will produce spurious counterexamples, obviously, when the non-deterministic values wouldn't have been possible with the original function body, and it may miss counterexamples if the function modifies globals. Generating better approximations of function bodies is one of our open problems. Now, note that the Havoc functions no longer contain any function calls, so we can now run the Reachability slicer to remove any newly unreachable functions. And I said that we allow configurations to the slicer to allow an engineer to control the imprecision that we are introducing. The first option is that we allow preservation of all direct paths or just the shortest path. In the example I showed you, there was only one direct path, but that's often not the case. And we prefer to preserve all direct paths because preserving only the shortest path is obviously more likely to miss counterexamples. We also add an option to preserve functions that are n function calls away from preserved paths. So here we have preserved functions that are one function call away from the direct path. Or we allow you to preserve functions by name. Here we have do not havoc do iret. Or to havoc functions by name. Here we have please havoc do iret. And so let's look at an overview of the full slicing algorithm. The first thing we do is remove the function pointers. Then we compute the call graph. We find the direct paths or the shortest path on the call graph. We identify the functions that should be havoced based on the configuration provided by the user. We havoc the functions. And then the final step before analysis is to run the Reachability slicer to remove the newly unreachable functions. And a final step that I alluded to, we want to start midway through the code, so we use a harness to approximate the starting environment. For instance, if we wanted to start an analysis at x86 emulate, we want to initialize these arguments to be something reasonable. We at least want the pointers to be valid and not void pointers. And we can also use these harnesses to incorporate engineer knowledge in the form of modeled functions or to restrict the possible values for the input parameters. In practice, we were actually able to start most of our XSA analyses at a harness we built that represents the Hypercall table. So the guest operating system uses hypercalls to invoke operations in Xen, and so we created a harness that is a non-deterministic switch that can call any hypercall that is available to the guest with non-deterministic input parameters. Okay, so can we use CBMC now? Well, yes, we can. So we ran on 5 XSAs with a set of slicer configurations for each XSA. We threw all of our experiments up on AWS batch, and all of our runs terminated within an hour. Many of them were much faster, and all of them produced counterexamples. But you noticed we made a lot of approximations. So we need to be aware that CBMC might produce spurious tracers if the modeling is wrong, or because the Havoc-ing is over-approximate, or because the function pointer assignment is over-approximate because we didn't analyze the boot code. We also need to be aware that we might miss tracers if the modeling is wrong, or if the Havoc-ing under-approximates relevant behavior, so writing to globals, or if we decided to not preserve all the direct paths. But in practice, well, actually, this didn't really happen. We ran on 5 XSAs, and of 4 out of those 5 XSAs, the counterexamples were useful for test generation, so they corresponded to an actual trace that could trigger the vulnerability from the start point. And in the case where the counterexample wasn't useful, it was because it provided only 50% of the trace needed to trigger the error. So the actual trace involved multiple hypercalls, and the first hypercall set the state of some specific variables that were then used by the second hypercall, and our counterexample only included the second hypercall because the specific variables were assigned to be non-deterministic in our starting harness. So what is the potential workflow now? Well, the engineer gives an assertion and a configuration to the slicer, runs CBMC, generates a counterexample, and then this counterexample can be used to generate a security test, and the engineer can determine whether this counterexample is valid or not. We're not able to fully automate our security experts, but we can provide them with some tools to help them do their jobs quicker. And there are plenty of open problems, including automatically verifying whether the counterexample traces are valid, synthesizing better function approximations, and automatically generating these harnesses for the XSAs. So in conclusion, we use CBMC to triage the severity of security issues in the Xen hypervisor, and although this work isn't complete or sound, it is useful. And we think the adaptations we made will be transferable to other code bases. We also hope that other people will be interested in engaging with the open problems we've presented, and also in using our adaptations to try to apply model checking to other industrial-sized code bases. Thank you for listening. If you have questions, please contact me. If you'd like to use our CBMC adaptations, they're available in the main branch of CBMC, and if you would like to run our experiments, the scripts are available on GitHub.